So our next talk is from Tom Bowe. Tom is a software engineer in the Lawrence Livermore National Lab Climate Program and a member of the Energy Exascale Earth System Model, E3SM, and Simplifying ESM Analysis Through Standards, SEATS projects. He contributes to numerous open source scientific software for climate science, including leading the development of the Xarray climate data analysis tools, xCDAT, which we'll hear about today. He's formerly a member of the Earth System Grid Federation ESGF project, where he was the lead full-stack web developer for Metagrid, ESGF's next-generation search portal for climate data. His interests and expertise are in scientific package development, full-stack web development, and DevOps engineering.
Thanks, Max, for that beautiful introduction. Hey, everybody. Can you hear me? Cool. All right, so appreciate everybody's time. I'm very excited to be talking about Xarray climate data analysis tools. It's a Python package that's been in development for the past 3 years. So my goal with this talk is just give you an introduction to this tool and also the process of how we came about developing it, as well as give a technical demo of some of the capabilities. So if you're interested, I'll give you like 10 seconds to scan this if you want to just follow this afterwards. It's a Jupyter notebook, so it's actually executable. You could go ahead and run the cells and stuff afterwards and play around with the notebook. In this format, it's a presentation though, so everything's pre-executed for this purpose. Sorry, should have made that like gigantic. So you got to zoom in. All right, I'll give it 5 more seconds. All right. So let me just skip this. Max already gave an introduction about me. So next slide. Just before I begin, I want to give a big shout out to my wonderful team. Without them, this project would not be possible. So Steve Pochetti, Jason Butte, Jill Zhang, and Jiwoo Lee, they've been great help on this project from the beginning. And as well as the people listed below, Peter, Paul, Carl, and Chris. They are climate scientists in the LLL climate program, and they've provided very good domain knowledge for us to be able to develop these capabilities for the climate community. I already mentioned this, but what I'm going to do is talk about the grounds-up development of a Python package and gear it towards climate science. So that's exactly what this project is about. So I'm going to talk about the driving force, the problem statement of how we actually started xCDAT, and so the scope and mission of the project. So what exactly are we trying to accomplish? We're also going to talk about the design philosophies, so how we actually design the APIs and stuff in a way that allows users to interface with the software in a clean and easy way. And we're also going to give a demo. I already mentioned that we're just going to go over some of the features, see how it looks in action, and get a sense of how things might look like if we're going to use it. And we're going to talk about parallelism with Dask. So Xarray supports parallelism, and we just want to see how xCDAT interfaces with Dask as well. And finally, how to get involved with the project if you're interested. So basically in climate science, if you're doing data analysis, there's a number of core operations that are typically required to analyze data. So first, reading and writing that CDF file, pretty basic I/O. Next, regridding. So you want to have you have a certain set of data, you want to regrid it into another grid in order to do comparisons across data sets, different models. This is another key feature that should be in an analysis package. And then spatial and temporal averaging, so doing geospatial averaging over regions, or calculating climatologies, calculating anomalies. These are also very important in climate science. Not only you need these features to be available, you need them to be highly performant. So being able to operate on growing volume of data as the models become more advanced as the years progress, right? So the resolution of models is growing every single year. Capabilities are just becoming more advanced. That just means that the data size is just going to be, it's just going to not ever stop growing. And you need to be able to have the hardware and the software to be able to analyze it efficiently. So there's a package. I'm not sure if anybody else is familiar with it, but xCDAT is a package that's been around for over 20 years. It's been in the climate community, and it provided open source visualization and analysis tooling. It was originally developed by developers from LLNL, And the issue with having this package, in the current day is that it's no longer being funded just because of the age. And naturally, software, as time goes by, you need either to refactor it, make sure it's up to modern standards, or find a new solution. So we decided to, instead of trying to rebuild on top of xCDAT, we wanted to pivot away and gather the great components of xCDAT and develop a new analysis package. So that's where xCDAT comes in. It combines the power of Xarray, so a modern, stable technology, with features from xCDAT that aren't readily available in other packages in the community. So general goals. First, as I mentioned, we want to offer core capabilities of xCDAT. That's things like regridding, temporal averaging, so on. We want to offer, make sure that it's on modern technology. So Xarray is one of them, Dask for parallelism. It has to be capable of handling large data sets. And we want to make sure that it's maintainable, extensible, and easy to use. So following modern software engineering principles, things like Python enhancement proposals, I'm sure everybody here is familiar with that. And by doing so, we want to encourage reproducible science. So the code should be easy to implement and easy to read as an end user. And finally, this is a major point that I want to drive forward, is we want to foster an open source community. So not only do we want developers from the lab and fund it from DOE, so it's a DOE funded project, we want others from other organizations to actively become a part of the development process. So that's interacting with Pangeo, ESGF, other orgs in the community. And now we're going to shift over kind of more on the technical side. We're going to talk about Xarray and why we chose Xarray as the core technology. First, it's mature and widely adopted. So it's a ton of stars in GitHub. I'm sure a lot of people here are using it right now. Next is fiscal funding from NumFocus. So it's stable. It's funding for years to come, as long as NumFocus continues to sponsor it. It also introduces, as far as the technical side, it introduces labels on arrays, which makes it really easy to work with compared to just referencing like axis numbers and stuff like that when you're doing a grouping operation. This makes the experience much more intuitive, concise, and just a pleasant experience overall. Key features, so I'm not going to go through this extensively, but file I/O, grouping, parallelism, some of the core things we were looking for from the get-go. And then supports NetCDF, Iris, OpenDAP, and it's also interoperable with a ton of tools in the scientific Python ecosystem. So if you need to use other tools for different scenarios, you could easily do that in Xarray and then convert over to another tool. And now we're going to kind of pivot over to xCDAT more specifically. So the team is composed of climate scientists and software engineers from E3SM, PCMDI, and SEATS. We are not only developers, but we're also users of it. So we integrate it in other packages that require analysis software, and there are scientists who actually use it for their research work. So it's kind of a back and forth of how we develop, which makes it really good for feedback, and it's feedback-driven development. So I already mentioned it's focused on routine climate analysis operations and leverages other Xarray-based packages such as XCSMF, XGCM, and CFXarray. So here's a general list of the features that we have right now. First is the extension of the Xarray OpenMF dataset and Open dataset. It has additional post-processing options for climate-specific data, such as centering time coordinates, converting longitude axis orientation, as well as generating missing bounds. So the generating missing bounds is more general, so it's not really climate specific, but it's really useful in climate data analysis because we use it for generating weights, which makes calculations more accurate and robust. So we also use the CFXarray package for CF compliant metadata, basically interpreting the metadata on data sets to ensure that they follow a specific standard, which is CF. And that allows us to operate generally across different data sets regardless of the source model. So as long as the data set is CF compliant, xCDAT should be able to interpret the metadata and run things like temporal averaging, climatologies, departures, and recognize the dimensions to operate on pretty seamlessly. I already mentioned horizontal regridding and vertical regridding are part of the package as well. So the software design philosophy, we encourage software sustainability and reproducible science. We want to make sure that things are well documented. So if you read the docs, everything is pretty extensive as far as API references. There's a ton of notebook examples to run the features if you want to just see how to use it in real world use cases. And finally, we want to contribute to Pangeo's effort of maintaining an ecosystem of mutually compatible geoscience packages so that when you're using xCDAT, you want to use another tool, things are working in line as long as they're Xarray based, obviously. So we're just going to do a simple example comparing xCDAT to some raw Xarray code for calculating global mean monthly anomalies. The purpose of this is just to compare how difficult it might be to do in Xarray and like how inflexible it is compared to just running a single line in xCDAT. So here, I'm just going to go ahead and open up a data set. It's a really long URL. I'm using a ESGF data set here. On the left is Xarray, so hopefully it's clear enough, but it's a 4-step process here. You could see we're opening up a data set, calculating the monthly departures, computing the global average, and then calculating the annual averages from the global average. So this is how many lines it takes typically to calculate that. So there's a lot of boilerplate here that could be, which we essentially just moved over into xCDAT and really cleaned up and created an API out of it. So you can see how here there's time.month. We're referencing the label and the month of the time dimension. Here, you're doing time again. So there's things that could be easily just done underneath the hood. So in our case, in xCDAT, it's a single line that takes all 3 of these lines and creates an API out of it. And if you look on the right, it says frequency. You could change the frequency. So instead of month, you could do day, you could do year, and you don't need to change all these labels every single time. Same thing as far as global averaging and annual averaging. The global average, you're going to do this NP cos, and then the degree to radian, and then as well as the weighted and the weighted mean down here. And now it's all encapsulated in an API. As well as group average, you're going to do that as well in the single line. Just some sanity check, just to make sure the results are the same. I'm just comparing them side by side so that you get a visual of the Xarray implementation against xCDAT. It's virtually identical on the plot. You could do some floating point analysis just to get the real baseline results. They're going to be really similar. And if you want to use xCDAT, it's all available on Conda Forge. Really easy to install. It's a standard way of typically installing Conda packages. And the documentation is here as well. So how to use xCDAT. So if you're going to, let's say, open up an Xarray object, you're going to start with Xarray as the base. There's a dataset object. You chain the spatial accessor as an example. There are a bunch of accessor classes, which are namespaces that encapsulate similar functionalities. So in this case, spatial, we're encapsulating the average method as well as the get weight methods. So that's going to be under this namespace. In this example, we're doing a dataset.spatial.average. It's super easy. It's straightforward and really readable. And there's a bunch of other accessor classes here. So there's temporal, regridding, bounds. These are all available within the dataset object, as long as you import xCDAT. So import xCDAT, open up a dataset. Now you have access to all these functionalities. There's also general utilities as Python functions. So these aren't bounded to a dataset object. They're just general functions you could call. So for example, say center times. You just pass in a dataset to it that you've already opened, and it'll center the time for you. And then there's just general functions that are, to help you in other portions like regridding. So there's a create axis, create grid. These could be used for vertical regridding if you need to, downstream. So now that we have kind of a baseline understanding of the capabilities of xCDAT, I'll just do kind of a very, very simple end-to-end workflow of analyzing CMIP data. So we're specifically using E3SM v2 model CMIP data, and we're going to go through the setup code, so imports, we're going to do I/O, and then regridding, and then some spatial and temporal averaging. So you can see here, there's some other imports just for plotting and such, but the main one here is just this one line, import xCDAT as xc. And then after you do the import, we're going to open up a data set. So hopefully it's big enough. We're passing that data set path that I had earlier in another cell. We're passing it into the open data set function. And I'm chunking it on the time dimension just so that I want to make sure it's parallelized. I'm using auto because I didn't want to kind of mess with the chunks. But typically you want to figure out what chunk size you're going to use according to how the data is structured. So I'm just using auto in this case to make things easier in my life. And there's a really neat HTML representation here in the notebook. So you could, if you're in Jupyter, you could look at the coordinates and the metadata, the indices. It's really helpful just to see what the data looks like. So first one we're going to do is horizontal regridding. So regridding, as I mentioned before, is really useful for making sure that data sets across different models are aligned. You want to do some cross comparisons. In this case, we're going to do regridding from a 1 by 1 degree grid to a 4 by 4 degree grid. And the first thing we want to do is create a target grid. So we're going to create two axes, the x and y axes using xCDAT's create axis function. And then we're going to create a grid from it. So we're going to pass those two variables that we created here, nlat and nlon, and we're going to pass it to create grid. And now we have a grid, which is a dataset object. And you can see here 90 longitude and 45 lat. So this is basically what we defined up here in these two variables. Now we're going to take that grid that we just created and pass it to the regridder.horizontal method. So as you can see, this is the accessor class, and this is the method that we're calling. And we're specifically operating on the TOS variable, which is near surface air temperature. The ngrid variable is passed here, so that's what we just created. We're going to do xcsmf and method bilinear, so bilinear regridding. And since we opened the data set with chunking, it's going to be parallel. It's going to be operating on Dask arrays. So when you're going to run any type of computation, even in xCDAT, you want to make sure you call compute, which will execute the task graph in Dask and actually give you the result. Otherwise, if you don't do that, it will just show you the representation of the queued up task and not actually run anything. So we've ran compute here, and this is the result we get. After regridding, you can see 4590, so it's performed the regridding. And finally, we're just going to show the plot. So pretty long plotting code. That's probably like the hardest part is running plots, to be honest. I always have a hard time, but for this sake, we're just going to show side by side. Original plot is right here, and you can see now we've done a 4 by 4 degree regridding, and you can see how much coarser it is as a result of calling that method. Next, we're going to do some vertical regridding. We have some cloud fraction data. We're going to regrid it from model hybrid coordinates to pressure levels. We're going to open up another data set this time, chunk it on automatically as well. And then, go back. And then we're going to call the vertical regrid method down here with these arguments. So new pressure grid as the output grid. That's what we create using the create grid method right here. And as far as the target data, we're creating the variable pressure data using this function. So these are A, P0, B, PS. These are found in the data set. We're extracting them. We're going to use those model hybrid coordinates to create the pressure data right here, as you can see. So that's our target data. And down here, as I mentioned, we're going to call it the vertical method. We're going to pass all those into that method, run compute, and once again, so we have the plotting result of the first time step. I also call it the spatial average just to average down to make sure the plot renders correctly so you could see the difference in how the vertical regridding actually performed. Next, we're going to do spatial averaging. So this is a common method to reduce dimensionality and spatial geospatial data sets. So we support both global area averaging and also specific regions. So you could define specific constraints like the lat bounds and long bounds so that it centers on specific regions that you want to average over. And it's weighted, so depending on the region that you define, it will be weighted as well. In this case, we are going to calculate the near surface air temperature of the Niño 3.4 region. We're going to specify lat bounds -5, long bounds 190, 240, and we're going to keep the weights. So that way we could just plot the results and see the weights side by side with the actual plot. It's also one line, so it keeps things simple. You don't need to code all those things, the like 4 or 5 lines that you saw earlier. And here's the result. Hopefully that's big enough. Try to zoom in. So this is the near surface air temperature of Niño 3.4 time series from 2000 to 2015 for this data set. And the weights, so this is since we specified bounds here, this is the weight of that region. And the dark blue is full weight. And as you so grid cells that are partially within a region will get partial weight. If it's fully within the region, it'll get the full weight. So that's just kind of how it works. And just a quick run through of some temporal calculations. So we're going to calculate seasonal mean climatology for that same variable here and plot the results. So you could see DJF, MAM, JJA, SON. So we've calculated the climatology for each season, and this is the result. And then there's anomalies. So calculating anomalies, it's a way to get the difference between a value during a given time interval and then and the long-term average for that interval. So like say you have a January, you want to get the average of the January and then get the average over the long term of all the Januaries for the last 30 years, right? This is a great way to compare the results from one year across all the years. In this case, we're gonna do historical era departure, so we're calculating a specific reference period. This would be 2000 and 2009, so it's about 10 years, 2010, if this is the last day, so. And this is the result, as you can see, this is based on the reference period, so it's not the full 15 years. And finally, just some quick overview of general dataset utilities. We're going to reorient longitude bounds and add missing bounds. So pretty straightforward, nothing too crazy here. As you can see, longitude axis was originally on the 0 to 360. Now it's in -180, 180 just by calling one function. Typically, this requires about 5 lines of code in Xarray. And you can implement it in different ways too. I've seen on Stack Overflow like 10 different ways of doing this. So this just makes your life easier just to call one function. Finally, adding bounds. So bounds, I mentioned, are really critical for weights to make sure that they're robust. The averaging observations are robust and produce accurate results. So xCDAT emphasizes adding missing bounds if possible. If bounds already exist, then they will just be used. But in this case, we're going to drop some bounds and then generate some new bounds for the t-axis. And as far as the t-axis, so time axis, it could either generate using midpoints or the time frequency, depending on what you need. So if it's midpoint, it'll use the difference between 2 coordinates and take the middle. If it's by frequency, let's say you have a monthly frequency, it'll take the first day and the last day and calculate the bounds that way. So there's 2 methods of calculating bounds. And that's to ensure, based on how your data is, you want to make sure that it aligns with whatever you need in your specific case. Quickly run through this, parallelism with Dask. So there's Xarray supports indexing, computing, and all that. All those core operations, they're all parallelizable. And xCDAT inherits that out of the box just because it operates on dataset objects. In this case, I'm opening up an 11 gigabyte dataset, chunking it 10 times, and also by 1 time. Just compare the run times here. And you can see on the left, it takes about 1:59 for the wall time here on the left for parallelized, and then 2 minutes and 37 seconds. You could probably chunk this better. I just did it by 10 just to show a quick example, but in this case, we're just demonstrating the parallelizability of xCDAT. And this is just show xCDAT outperforms CDAT, the older library, which is sequential only. If you're interested, you can check out the plot on the notebook. And if you're interested, here's all the resources for xCDAT, and let's see what else. Future plans, we're going to collaborate with Xarray, continue assisting DOE-funded projects to migrate over to xCDAT, and also explore Xarray data tree, which is a Xarray package for ensemble analysis. And if you're interested in contributing, these are all the links. You can scan that really tiny QR code. Yeah, I tried to make it bigger, but it wouldn't cause my thing to like scroll down, so try that out. And there's a bunch of links here. So thank you for everybody attending, and I appreciate your time.
Alrighty, we'll open it up for questions. Do we have any questions in the room? Otherwise, in Slack, especially for remote attendees, you can go ahead and ask there. So I see one over here.
Yeah, a very, very nice talk. And, you have like high-level wrapper around Xarray, make the average like very, very easy to handle, right? But I'm just like a little bit, interesting, like the flexibility we may be losing. Like, for example, you're doing spatial averaging, right? So depending on the way the data is chunked, right? So if you go lat first followed by long, and maybe different, the performance may be different from long versus lat, right? So do you handle this optimization automatically, or it's just based on certain order? Okay, this is my first question. And second real quick one is, okay, yeah, it's gonna be a quick one. Okay, so for different data format like Xarray, like for example, if we are trying to make our metadata follow the CF convention, does xCDAT or now or in the future plan to make it work? Thank you.
Yeah. So for the first one, so we kind of put the responsibility of chunking on the user, just because the data sets are, they could be different wildly in how they're structured. So the user needs to figure out how to chunk their data set initially before they call xCDAT computational operations. xCDAT does not automatically chunk things for you unless you specify auto, which doesn't always do the right thing. So you need to make sure that when you know your data set and how it's structured, and then chunk appropriately before you call anything. And that's just generally how Xarray operates too, because you want to make sure in Xarray, if you're doing anything in Xarray, you chunk it properly. And then your second question, if I'm getting right, it's as long as things are CF compliant, xCDAT should be able to operate on it. Is that what you're trying to ask? Yeah, so that's true. So as long as xCDAT or the data sets have the metadata in CF convention, then xCDAT can interpret the metadata properly, and then map to the right dimensions and do the averaging operations for you. So you don't need to specify the exact label names. xCDAT will know the exact label names to use because it has the metadata already built in. So, yeah.
So we have a question from online, from Kevin. Is there an expectation of regularly gridded data, or does this also handle irregularly sampled observations?
So this is specifically structured grids. There's UXArray is a package I mentioned that is for unstructured grids. So anything rectilinear, curvilinear, that's what xCDAT handles. We try to keep it very scoped and focus on just structure.
Great. Any other questions? Yeah.
How different is xCDAT from the CDAT API, and what was the process like of migrating any users of CDAT to xCDAT?
Yeah, so the CDAT API is we tried to get some of the naming conventions the same, but they're wildly different. They're not the same at all. And as far as getting users over from CDAT, so CDAT was originally developed at the lab, and xCDAT partially is developed at the lab as well. So we already had a core user base that we could transfer over as the initial users. And then that allowed us to kind of branch out and start reaching out to others as this product, the software is being used internally, right? And now we're at a state where it's pretty mature, and now there's organizations all over the world that's trying to use it, which is a really good sign.
Awesome. Well, thank you so much.
Yeah. Thank you, everybody.